Hello and welcome to the third and final part of Lecture 15. We're going to be doing some examples of concave and convex mirrors. So we're going to look at example 1, where we have a convex mirror, a spherically convex mirror. So this is a mirror that is curved outwards. And we're told that an object is 2 centimeters tall and it's placed with its base along the optical axis of a spherical convex mirror. We're given its focal length of 4.5 centimeters. And then the object is moved from position of 1 centimeter inside the focal point to position 1 centimeter past the focal point. Past the focal point. And by what factor does the magnitude of the magnification of the image change? Okay, and again, let me put the T in there. Okay. All right, so quick picture of this. And I won't try to draw it too much, but just kind of a rough sketch is we've got our convex mirror. We'll have our optical axis like so. We're then going to have an image, an object that is located somewhere over here. Okay, and then we know we're going to have the focal point. Okay, so object axis spherical convex mirror with a focal length for the object is moved position 1 centimeter inside the focal point to position 1 centimeter past the focal point. So you might be kind of wondering about the way this is phrased, and I want to give some explanation to that, because obviously the focal point is here, okay, and that's where it is for a convex mirror. Now the thing is that distance, however, is often referred to on both sides, and that's the case in the wording of this problem. So even though the focal point, for the purpose of drawing those principal rays, is on the inside of the mirror, okay? So it's on the opposite side of the mirror from S, because that'd be the distance here, would be S. We can still draw the focal point outside the mirror as well. In other words, on the same side as S. We wouldn't use that for drawing for principal rays, but its coordinates are still relevant. It's just kind of the negative x value. Its magnitude is relevant on both sides, even though it has a particular side that's used for drawing principal rays. So what that means is we can have f over here as well, okay? And that of course then has the problem makes sense in terms of having it be 1 centimeter inside and then 1 centimeter outside. So the initial location of our object, so let's right, so we'll copy it. So initially it's inside the focal point by 1 centimeter, and then it's outside the focal point by 1 centimeter. Okay, so this is just our two locations. All right, and so then we'd have S, and then S, kind of S and S naught, right, where it started and where it ends up. All right, so I'll label that as S naught, this shorter one. All right, and then in both cases there's going to be an image formed, which would be our S prime, and then we just want to talk about how those images are going to differ, but importantly how they're going to change the magnification. Okay, so in order to do this, we want to just kind of start working with the formulas for spherical mirrors. So we know we're going to be using this formula. We're going to be using our 1 over S plus 1 over S prime equals 1 over F. This is definitely the formula we go to for any spherical mirror formula or problem. In this case, we want to find S prime, okay? And this will be S prime naught, because I'm going to do this for the case where we start off with it inside the focal point. All right, so what would that look like? So let's kind of first plug in our numbers, and then we'll kind of set it up to solve. I take that back. Let's just go ahead and set up the solve first. So I have 1 over S prime naught, so keep it symbolic in other words, and then 1 over the focal length minus 1 over the object distance. Okay? Good. All right. And then we want to solve for S naught prime. All right, so we're solving for the initial location of the image. And then that's going to be 1 over F minus 1 over original object length to the negative 1 power. So because that got rid of the reciprocal. Okay. And so then I'd have a 1 over, okay, and then my focal length is given as 4.5 centimeters. But here's the thing. It's a convex mirror. And I know for convex mirrors, focal lengths are always defined as negative. Always. Whereas for concave mirrors, focal lengths are always defined as positive. And that's because even though I've, drew the focal point on both sides, the effective focal point for the convex mirror is on the opposite side of S and is defined as negative. As anything that's on the opposite side of the mirror from S is defined as negative. Okay, so that would be negative 4.5 centimeters. And I'll keep it in centimeters, so I'll get my final answer in centimeters. And then subtract 1 over S naught. Now S naught is the length of the object. Well, the length of the object sets the negative and positive. So S is always positive because it's the convention. Okay? And so that we're given as, if it's inside, then be 3.5. Right? Because it's 1 centimeter inside of the focal length. So it's 1 centimeter less than 4.5. Okay, and so that's going to give me my first object length, which is negative 1.97. Okay, and then when I do it for moving it 1 centimeter outside the focal length, so then I would have S prime is going to be 1 over F minus 1 over S, as opposed to S naught, because that's the bigger one. Okay, and then still to the negative 1 power. And so that would be 1 over negative 4.5 centimeters minus 1 over 5.5 this time. Because it's now 1 centimeter past. I forgot the negative 1. There's negative 1. Okay, and so this gives me negative 2.48. So in both cases, I ended up with a image. Both times they're negative, which means both times they're inside the mirror. And so if I was to draw them, they'd look a little something like this. All right, so I'd have, for the first case, that one is has a smaller S. So it would be an image somewhere over here. And then another one has a bigger S, but still smaller than F. So it'd be over here. Okay? So what about their relative magnifications? So they actually made them too big, both of them. Let's draw them a little bit smaller. So here's the first one like that, and then the other one would probably be something like this. Okay, so those are the two images. All right, and so let's go ahead and just find both their magnifications. So continuing then with part A, we have M naught is then just going to be negative S naught prime over S. All right, which would be negative of negative 1.97 centimeters, and then divided by S, which was 3.5 centimeters. Okay, and so then that has a magnification, which will be positive because the negatives cancel out, of 0.563. So how do we interpret that magnification, right? Because I showed you the formula in the previous video, but the interpretation is so key. Well, again, the sign, the fact that it's positive, tells us that we have a magnification or an image that is upright, which also tells us the image is virtual. The fact that the value is less than 1 tells us that our magnification is shrinking. So magnification doesn't mean enlargement. Magnification just means change in size. If your magnification is 1, as is the case for planar mirrors, that means there's no change in size. You look at the mirror, you're the same size inside the planar mirror as you are in real life. But when you look into concave and convex mirrors, the image can be enlarged or shrunk. Any value less than 1, it was shrunk. Any value larger than 1, it was enlarged. Both of those are termed as magnifications. So we'll add a couple notes here. M less than 1 means image is shrunk relative to the object, and m greater than 0 means image is upright and virtual, which if you know one, then it has to be the other. Upright means virtual, but just for clarity, I'm writing both. Okay, and then let's do the same thing for m. So m would then just be negative s prime over s, or negative times negative 2.48 centimeters, which I left off there, divided by 5.5, which gives us 0.45. Okay, so the ratio changes. It always does. Okay, so then the magnification decreased by a factor of 0.8. So we can say, thus m2 over m1 equals 0.8. So that was the answer. And kind of what that means is that the factor of magnification is decreasing. So image is getting smaller as s increases, right? So as the object distance gets bigger, as the object gets further from the mirror, the convex mirror, the image becomes more and more shrunk. And part B, I asked, does the type of the image change? Well, no. And in fact, we would know that without even checking for the fact that there's no sign change, because we know that convex mirrors only create virtual images. So there's no case, unlike with the concave mirror, where moving that object back and forth can actually have the image type change from virtual to real or from real to virtual. Here, that's not the case. So, no, both images are virtual. Because when we talk about types of images, when you see that keyword type, that's what it's referring to, either real or virtual, because those are the only two types of images in a general sense. Okay, so question 1, I definitely want to leave that for practice. I highly recommend giving it a try. This is just doing like what I did in the previous video on the key terms and equations page, where I showed you the principal rays. You would do the same thing for these two cases. So draw principal rays and use those principal rays to find the location of the image in both cases. Okay? All right. So then, if an object is placed at the focal point, here's question 2, this one I want to answer in the video. If an object is placed at the focal point of a concave mirror, where will the image be formed? Okay? So let's go ahead and kind of think about using the equation and what that tells us. Because we haven't talked about placing an object exactly at the focal point. We kind of talked about placing it inside or outside, like in the previous example. But what if you place it right at the focal point, in this case of a concave mirror? So consider 1 over s plus 1 over s prime. So object length, image length, both measured from the mirror, and then focal length. Okay. Well, in this case, we have s equal to f. So it would become 1 over f plus 1 over s prime equals 1 over f. Huh. Well, that means that 1 over s prime is just equal to 0. Oh, well, that's weird. That's telling us that our image must be infinitely far away. Thus, only s prime equals infinity is possible. So in other words, if you put your object exactly at the focal point of a concave mirror, and in fact this works equally well for a convex mirror, then you don't get an image. Your image is infinitely far away. You have a case where now there's nothing. Okay? And so let me think. I'll take it back actually, because for the in this not for this case, this is still true, but for the convex mirror case, in that case your 1 over f is negative, And so when you subtract both sides, you actually get 2f. So in that case, you still get an image. But for the concave mirror, placing your image exactly at the focal point means no image at all, neither real nor virtual. Okay? Unless you consider an image at an infinite distance an image, but really that means no image. No image. Okay? All right, so I want to do one more example and leave the rest for practice. I figure we should do a concave mirror, okay? Because we did a convex mirror in example 1. So we'll jump down to example 5. We have an object placed 19 centimeters from a concave mirror produces a real image 12.7 centimeters from the mirror. If the object is now moved to a new position 27 centimeters from the mirror, where is the new image located as measured from the mirror? Okay, so another quick sketch here. So this is our concave mirror. Do a bit better job than that. Yeah, passable. And here we'll have our optical axis. Okay, and so then we're going to have our focal point. Okay, and then we're going to place our object. So we're going to place it 19 centimeters. Okay, and then we have, so this will be our object, and I don't know where f is. I'm just kind of placing it there. This is my guess of where f is, and then I'm going to get a real image. Okay, and that one's going to be 12.7. So maybe something, if that's 19, maybe I'll bring 19 in a little bit closer, and then maybe have my 19.7 be somewhere over here, or my 12 to be somewhere over here. All right, and then let's label s and s prime. Okay. Okay, so there we go. So this will be, this here is S. This one's S. And then here we'll have S prime. There's our S prime. And how did I know to draw the, this image inverted? Well, I know because I was told that it's real. So it must be inverted. That's why I knew to draw it upside down like that. Okay. And so then actually starting with the problem, we're going to use the same equation. We got 1 over S plus 1 over S prime equals 1 over F. In this case, we want to solve for F. Okay. And so then we're going to solve for our focal length. So that's going to be 1 over S plus 1 over S prime to the -1 power. Okay. And both our S and S prime are positive because they're both on the same side, or it's really S prime that's positive because it's on the same side as S. Okay. And so then, because again, S is always positive, the object length is always positive. And so then we simply plug it in, leave it all in centimeters. So I have a 19 centimeters for S. I have a 12.7 centimeters for S prime, the image length. Okay, so that's going to give me my real focal length. Okay, so 1 divided by 19 plus 1 over 12.7 raised to the -1 power. All right, so 7.61 is our focal length. Okay, so I should probably move it because my guess was wrong. So let's move it over a bit. It's going to be more in here somewhere. See if I can kind of move it out of the way a bit. All right, and then I guess make it look like an F. There we have it. Okay, so there we have our focal length. Looks good. And we got our real image. Yeah, everything's coming out. Let me just consult something real fast. Does that make sense? Oh, yeah. Yep, because the real image is coming outside the focal length. That makes sense. Yep, that they're both, then it makes sense that both S and S prime are bigger than F. Yep, that's going to be the case. Okay. And then if the object is now moved to a new position of 20 centimeters, where is it? Okay, so now that we have F, we can then basically just do our step 2 here to solve for S prime. So we're going to again use this equation. This time we're solving for S prime. So S prime would just be equal to 1 over S minus 1 over F, the whole thing raised to the negative 1 power. So we have a new S now, it's the 27. So we have 1 over 27 centimeters. And then we'll have, or subtract, our focal length, which we now know to be 7.61 centimeters. It's the whole point of the first line of calculation. And then we'll find out where that new image is created. So 1 over 27 plus 1 divided, or minus 1 divided by our result from the first line. All right, so we then get a value of negative 10.6. All right, let's make sure that makes sense. So, sure correctly did everything by interpreting the answer. So negative 10.6, that's telling us that that is giving us a virtual image. Yeah, okay, so we have our, because we moved much further away. Yeah. And so now our image is ending up behind, would that really work? I mean, certainly it's just numerically it makes sense because the 1 over 27 is a smaller number because we're dividing, it's a bigger denominator, and so it makes sense that this would give us a value. Whereas before we had 19 and 12.7. Nope, just bad math. Okay, good. Because I'm like, I'm pretty sure, because the only way to create a virtual image with a concave mirror is to actually have the object inside the focal point. In this case, the object is still outside the focal point, just even further away. But I see what I did is just a stupid algebra mistake. So let's go ahead and fix this here. So this should be, if you think about it, I'm solving for S prime, so it's 1 over F minus 1 over S, not the other way around. Yep, and so this term is here, and this one's here. There we go. That makes a lot more sense. Okay, so let me fix that. Sorry for the typo. Well, like I always say, it's just testament of interpreting our answers rather than just, writing them down. And yeah, so it just changes the sign. So it is positive 10.6 centimeters. So now, basically now our S prime moved from 12.7 centimeters to 10.7. So actually, if you think about that you still might not be the result you expect, because you might think, oh well, look, I made S bigger. Shouldn't S prime be bigger as well? Well, definitely not, because actually what's happening is as you make S bigger and bigger, as you move your object further and further away, right? As I move it further and further away, I end up with an image that gets closer and closer to F. So you can see what happens in the limiting case, right? Is that as I make S really, really large, that means that this value is effectively going to 0, which means that S prime is just going to F. It's just getting closer and closer, right? So eventually, if the object is further enough away, its image is right at the focal point. And that makes a lot of sense. Okay, so we saw a good example of a concave mirror and a convex mirror, and you have some further practice where you can look at another convex mirror and also another convex mirror. Okay?